Assalamualaikum and hi everyone, this is Dr. Shazira. In this video, we are going to be discussing the shifted power method, which is used to determine the smallest eigenvalue. The steps of solution are as follows. Okay, so first we need a shifted factor. Okay, we need a shifted factor P, which is the lambda 1. Okay, so lambda 1 is the dominant eigenvalue. So before this, in the previous video, we have seen how we can determine the dominant eigenvalue by the power method. Okay, so that dominant eigenvalue, which we denote as lambda 1, is basically what we call the shifted factor P in the shifted power method. Okay, and then after that we need the matrix B, which is obtained by this formula here, A minus P times I. Okay, A is your matrix, okay, supposed to be given in the problem. P is again the lambda 1, okay, and I is the identity matrix. Okay, and then step number 3, use the power method to get the lambda B here. So lambda B is the dominant eigenvalue for matrix B. Okay, so it means that we apply, okay, what we have done earlier, the power method, but on the matrix B, not on the matrix A. Okay, what is B? B is given here in step number 2. All right, and after that we find the lambda n. Okay, so lambda n is the smallest eigenvalue. So if we have a matrix A which is 3 by 3, so your lambda n is supposed to be lambda 3. Okay, so lambda n is equal to the lambda B plus P. All right, and the associated eigenvector to the lambda n is given by Vn. Okay, so we know this Vn, okay, by the solution from step number 3 here. So when you get your lambda B, you also get the associated eigenvector to the lambda B. Okay, so Vn is approximately Vb. All right, so that's the steps of solutions in the shifted power method. All right, so next we are going to see one example on how we can apply the shifted power method. Consider this matrix A, which has the dominant eigenvalue lambda 1 is 12.285. So this is basically the same matrix that we have in the previous video on the power method. Okay, so the dominant eigenvalue is given here, lambda 1, and our task is to determine the smallest eigenvalue of matrix A, which we denote as lambda 3, because our matrix A here is 3 by 3, so we have the eigenvalues in terms of lambda 1, lambda 2, and lambda 3. So lambda 1 is the largest eigenvalue or the dominant eigenvalue. Lambda 2 is the middle, okay, it should be in the middle, and lambda 3 is the smallest eigenvalue. Okay, and we also need to get the associated eigenvector, okay, V3, by the shifted power method. Okay, so given to us here, V naught is 1 0 0, and then we stop the iteration when we satisfy this stopping condition here. Okay, and do all calculation in 3 decimal places. That's A. And in B, we need to calculate the eigenvalue lambda 2, okay, for matrix A based on the result in part A. So it is given to us lambda 1 here. So um, from A, we get the lambda 3, and then we need to get, lambda 2, which is the eigenvalue between lambda 1 and lambda 3. So there will be a specific or particular theorem to get the lambda 2 here. Okay, we will see after this. All right, so we start our solution process. Okay, here by looking at these steps of solution here, we need a shifted factor P. So P is lambda 1. So lambda 1 is already been given in the problem, which is 12.285. Now we need to get the matrix B, which is A minus PI. Matrix B is A minus PI. So this is your matrix A given by the problem. P is lambda 1. here, and this is the identity matrix. Okay, so A minus P times I, so this is P times I, and then you subtract A and PI, so this is your matrix B. Okay, and then next is to get the lambda B. So lambda B is the dominant eigenvalue for matrix B. Okay, so it means here you need to apply the power method, but now to the matrix B. You apply the power method to the matrix B, then you get the dominant eigenvalue for the matrix B, which denote as lambda B. So in terms of the formula, the power method formula would be Vk plus 1 equals 1 over Mk plus 1 times B here, because you apply the power method to the matrix B. So replace A with B in the formula, and then times Vk. Alright, so in terms of table, you are going to have K, Vk, and here you have B, Vk instead of A, Vk. Okay, and then Mk plus 1, and also the stopping condition here. So at the first row, okay, when k equal to 0, we can put the eigenvector, the initial eigenvector given by the problem is 1, 0, 0. Okay, so next, your computation start with this one here, BVK, and then after that you determine your MK plus 1, and then after that you can get your VK plus 1. That's the flow of the power method. So 1, 2, and 3 here. So we are going to use calculator to speed up our calculation. So we are going to store the matrix B as well as the eigenvector 1, 0, 0 here in our calculator. Use a mode matrix. Okay, number 4 for the matrix. Now we want to define the matrix B. Okay, matrix B here. So let's use the same notation. So use the mat B here. So number 2, choose number 2. Number of rows is 3. Number of columns also 3. And now input all elements of matrix B. Okay, one by one in your calculator. Okay, so that is your matrix B. Now we also want to store the eigenvector 1, 0, 0 here. So define under the matrix. So define matrix 1. Okay, so you can choose mat A, mat C, or mat D. Okay, so I'm using mat C here. So number 3, number of rows is 3, number of column is 1. Okay, for the eigenvector. So 1, 0, and 0. Okay, so that is your eigenvector. Now your computation start with the BVK. So in your calculator, call matrix B, which is 4 here, times your VK, which is your mat C in the calculator. So call 5 for the mat C. Okay, so now you have mat answer, which correspond to the B times V, okay, in your table. Now you have negative 8.285, and then you have 2, and the last element is negative 1. All right, now determine your MK plus 1. Okay, by looking at these three elements here, so look which one is the largest in terms of absolute value. So you see this guy is the largest in terms of absolute value, but when it comes to writing, you need to write the actual sign, so you need to put the negative. Okay, so negative 8.285. Okay, and then for the error here, we don't have the error yet because we only have 1 M for now. Okay, just put dash. Okay, so you are basically at step number 2. Okay, now since we already have our BVK, these elements here, and we also know our MK plus 1, now we can compute VK plus 1. So that's basically BVK divided with MK plus 1. Okay, so in your calculator, your current view in your calculator is actually your BVK. Okay, now you want to divide with MK plus 1, so you just press division, okay, button, and then your MK plus 1 is negative 8.285. Okay, so this new math answer basically correspond to this one here. In terms of table, it should be at the second row, because here, okay, what you have computed up to this row here is basically for k equal to 0. K equal to 0 here, k equal to 0. When you plug in, you will get V1 somehow. Okay, 0 plus 1. V1 is supposed to be at the second row. So the value should be here, k equals 1, and then you have 1, negative 0.241, 0.121 in 3 decimal point. Okay, that's one complete iteration. Okay, and then we proceed, okay, with the next iteration. So we start with a BVK. Okay, now your VK is this one here, which is your current math answer in the calculator. Okay, so B is the same matrix that you have stored earlier in your calculator. So we call for the matrix B. So 4 times VK. So VK is your current math answer in your calculator. So call math answer. So 1. All right. So you have negative 8.889 basically. Okay. And then you have 3.638, and then negative 1 point. So you need to scroll down here because we don't know, okay, what is the length of the third one here. So that one is negative 1.27, negative 1.276, okay, in 3 decimals. So again, okay, identify your MK plus 1 by looking at these three, which one is the largest in terms of absolute value. So this guy here, again, you need to take the actual sign. Okay, you take the absolute value just to identify which one is the largest. Okay, but when it comes to writing, you put the actual sign of it. So that value. Now you can compute the difference between two consecutive m. Okay, so this m here subtract with that m. Okay, so you can use your calculator here. So negative 8.889 minus negative 8.285. Okay, so take the absolute of this. Okay, so you have 0.604. All right, so this one is still greater than, okay, 0.604 is still greater than the given epsilon, okay, in the problem is 0.05. So it means we need to proceed, but up to this stage here, we are currently at this step here. So one complete iteration should be up to here. So we need to compute VK plus 1. All right. Okay, so K equals 2. All right. So BVK over MK plus 1. So BVK is actually this one, which is your current math answer in the calculator, and then divided with your current MK plus 1. So you need to call back your math answer. So number 1 divided with negative 8.889. Okay, so you have a new math answer correspond to the V at k equals 2. Okay, so you have 1 in 3 decimals, and then you have negative 0.409, and then you have 0.144. All right, so that one complete iteration, basically iteration number 2. All right. Okay, now we proceed with BVK. So call your matrix B times V. V is your current math answer in the calculator. So call matrix B. So 4 times your math answer. So 1. So you have now negative 9.246. Okay, and then 4.716. Okay, and negative 1.45, negative 1.450, and again your MK plus 1 in terms of absolute value. Okay, the largest element here is this guy. Okay, so your MK plus 1 is negative 9.246. Now compute the difference between two consecutive m. So negative 9.246 subtract with negative 8.889. So in terms of absolute value, that is 0.357. And then, okay, complete your computation. So step number 3. So you will have here k equals 3. So BVK, okay, your BVK is your math answer. Okay, your latest math answer in the calculator divided with this guy. So call back your math answer, divide with negative 9.246. So you have your VK, okay, K equals 3. So 1, then you have negative 0.510 and then 0.157. Okay. And then you proceed, okay, the iteration process until, okay, you see the stopping condition here. You satisfy the stopping condition here, which is the value here should be less than 0.05. Okay, so I hope you can proceed on your own. Okay, but for now you can see the complete values, okay, for this table. All right, so you are supposed to get these values here. So up to this stage here. So you see the difference between two consecutive m now is smaller than 0.05. So you know that you can stop here, but be careful. This is not complete yet, because up to this column you are actually at this stage. Okay, second step in your computation of our method here. So you need to complete your computation. Okay, so you get your VK plus 1. So your table should be, up to this row, k equals 7. Okay, so that is BVK, your current view in the calculator. Okay, so math answer here is this one here, BVK divided with your current MK plus 1. So complete your iteration cycle. So divided with negative 9.683. Okay, so you have 1 here, and then what is it, negative 0.623 somehow, and then you have 0.172. Okay, so that is the complete table. All right, so okay, now so the whole process here is basically to get the lambda b, but that is not our final answer. Okay, because what we want is the smallest eigenvalue for matrix A. So up to this point, what we have computed is actually the lambda b. Okay, lambda b, the dominant eigenvalue for matrix B. So we put here, so therefore lambda b, the dominant eigenvalue for matrix B, is approximately your m. So your latest m in the calculator here, in the table here, is this one. Okay, negative 9.683, which correspond to the m7. Okay, so even though this is 6, but this column is mk plus 1, so this value here is actually m6 plus 1, so m7. Okay, it should be tally with your eigen vector at the end here. So lambda b is approximately m7, so that is negative 9.683. So that is your lambda b. And the corresponding eigenvector is lambda b, which is approximately your v at k is 7. Okay, so that is 1, negative 0.623, and 0.172 transpose. Okay, now back to the next process in the shifted power method. So once you get your lambda b, so the next step is this one. Okay, find lambda n our n is 3 because we have 3 by 3 matrix. So lambda 3, which is the smallest eigenvalue, is given by lambda b plus p. Okay, so lambda 3 then. So therefore, lambda 3 is equals to the lambda b plus p. So your lambda b is negative 9.683. So your b is your lambda 1 given by the problem. So you have 12.285. Okay, so you have the answer is 2.602. Is it? Okay, that is your smallest eigenvalue for matrix A. And the question also asks you to find the associated eigenvector to your smallest eigenvalue. Okay, so you have the lambda 3. So the associated eigenvector is V3, which can be approximately VB. So your VB is 1, negative 0.623 and 0.172 transpose. Okay, that's your solution for question A. Now, for B, all right, so what is B? So B, calculate the eigenvalue lambda 2 for matrix A based on the result in A. Okay, so to compute lambda 2 here, we actually have two formulas, okay, that you can choose. Okay, it's up to you. But if the question asks for a particular formula, then you need to follow. So what is the formula? We have two formula correspond to the eigenvalues. The first one is lambda 1 plus lambda 2 up to lambda n is equal to a11 plus a22 up to the a(n)n. So what you have at the right hand side here is basically the elements at the diagonal. So a11, a22, and so on. So this is the diagonal elements of your matrix A, and this is your eigenvalue. So since we have 3 by 3 matrix, so just now we have lambda 1 given by the problem. We have computed our lambda 3. So in between, we need to get lambda 2. Okay, so of course, A11, A22, A33 can be identified, okay, from your matrix A. Okay, so we can use formula number 1, or formula number 2 is this is what we call the trace. Okay, lambda 1 times lambda 2 times lambda 3 in the case of 3 by 3 matrix is equal to the determinant of A. Okay, so you can use your calculator to get the determinant of A, and then lambda 2 is basically is the determinant of A divided with lambda 1 times lambda 3. So you can choose any of this formula, but if the question asks for example, a particular formula here, then you need to follow. Okay, all right, so I'm using formula number 1. All right, so therefore our lambda 1 is 12.285. Okay, and then what we want to compute is lambda 2 plus our lambda 3. So just now your lambda 3 is 2.602, okay, is equal to, so now this is the diagonal element for your matrix A. So look back at your matrix A given by the problem. So the diagonal element is this one. So this is A11, A22, A33. So 4, 6, and 12. All right. So 4 plus 6 plus 12. Okay, so just simplify, okay, rearrange the expression plus minus here and there, you can come out with your lambda 2. So what do we have?